In this lecture, we will be covering the topic of computation of area between polar curves. So we will be thinking about a region bounded by radial lines, theta equals alpha, and theta equals beta. And then we will have two polar curves, r equals f of theta and r equals g of theta. So r equals f of theta, we are going to call the outer curve, and then the inner curve will be r equals g of theta. And to make this easier, we're going to call r equals g of theta r inner, and r equals f of theta r outer. We are concerned with the area bounded between these two polar curves, r outer and r inner, and these radial lines, theta equals alpha and theta equals beta. To think about how we compute this, we recall that we know how to find the area bounded by theta equals alpha, theta equals beta, and this blue curve we're calling r inner. And recall that this area so the inner area is equal to the integral from alpha to beta of 1/2 times this r inner squared d theta. This coming from our previous lecture about area computations in polar coordinates. When we take into account our outer curve, well, we know that this area we will highlight in yellow. We can use the same type of calculation to argue that this larger area, or the area associated with the outer curve, and again these two radial lines, is the integral from alpha to beta of 1/2 r outer squared d theta. And of course we can see visually that the area that we are after, the area bounded by the radial lines, the outer curve and the inner curve, is the difference of these two. The area that we seek is this a outer minus a inner, or the integral from alpha to beta of 1/2 r outer squared d theta minus the integral from alpha to beta of 1/2 r inner squared d theta. And using linearity of integration, we combine that difference of integrals into the integral of the difference, and we arrive at this formula for our area computation. And generally, the way to think of this is if you have this polar area, so the area, the kind of area we were looking at initially, the way to identify the terms here in your area formula can come from taking a ray, starting at the origin, at the pole, and sending it through the region. You can identify R outer by the curve on which it exits the region. And you can identify R inner by the curve via which this ray enters the region. And your angular range can be thought of as the range over which you need to sweep this hand. Think of it like the hand on a clock. What's the range over which you have to sweep this hand such that this piece trapped between R inner and R outer, this piece of this ray, as you sweep this clock in this counterclockwise fashion over the region, that will sweep out, this piece here will sweep out the area of concern. So for example, suppose we want to find the area of the region inside of the graph r equals 2 sine of theta, and outside of the graph r equals 1. R equals 1, we know, is the circle of radius 1 centered at the origin. R equals 2 sine of theta. Well, we can think about what that looks like. R equals 2 sine of theta looks like it would be easier to handle if we multiply both sides by r. And then think about changing it over to Cartesian coordinates. And we know that r squared can be written as x squared plus y squared. R sine theta is y. And so this becomes x squared plus y squared minus 2y equals 0. And if we complete the square by adding 1 to both sides, we see that this is x squared plus y minus 1 squared equals 1, which we know is a circle of radius 1 centered at the point 0, 1. So this is the center of that circle. It has radius 1. So we know this other curve will look like so. And the question is asking us for the area of the region inside of r equals 2 sine of theta and outside of the graph of r equals 1. And so the area that we seek is this piece here. So thinking back to the strategy that we just discussed on the previous page, we take a ray emanating from the pole, from the origin, and send it through the region. And we check where it enters and where it exits the region. And that will help us identify our R outer and our R inner. And we see from this that R outer is the circle centered at 0, 1, or 2 sine of theta, and R inner is 1. So this gives us our integrand. We now need to find the range for the angles. And we know the idea here is to take this ray, put it at the beginning of this region, and sweep it, turn it counterclockwise so that this piece that's trapped between R inner and R outer sweeps out the region one time. And that means we need to find these points of intersection. Because we will want to start this ray here, going through this point of intersection, and then sweep it counterclockwise until it hits this point of intersection. So we now need to solve for these 2 points of intersection. To solve for these intersection points, we can use the fact that our outer curve has equation r equals 2 sine of theta, and our inner curve has the equation r equals 1, and we're looking for the intersection of these 2 curves. And we can try and find them algebraically by setting 2 sine of theta equal to 1. Or sine of theta equals 1/2. So our question is now, what angle theta has a sine that is 1/2? And we need to remember one of our right triangles where we have sides 1, 2, √3. The larger angle is pi over 3, and the smaller angle is pi over 6. And using our SOHCAHTOA rule, we can see, since sine is the opposite over hypotenuse, to get a sine of 1/2, pi over 6 will work as an angle. And given the symmetry of this picture about the y-axis, if this angle here is pi over 6, we know that this angle over here, that this radial curve makes with the negative x-axis is also pi over 6, which means it's going to be characterized by theta equals 5 pi over 6. So these are the equations of these 2 radial lines. And they tell us the starting and the ending value for our theta. So we use theta is pi over 6 for our lower bound for our angular range, and we rotate over to theta equals 5 pi over 6. Putting this all together, we, to get our area, integrate from pi over 6 to 5 pi over 6 of 1/2 times the quantity r outer squared minus r inner squared, using the formula that we derived earlier. And for this question, we can see, if we simplify a bit, we get this integral, and we need to use techniques of integration that we typically learn in our introductory integral calculus course to solve this integral, which we leave as an exercise. And the solution that you will arrive at is 4 pi plus 3 √3, all divided by 6.